Welcome to the deep dive. We take complex ideas, boil them down, and give you the core insights. Today, we're jumping into a really fascinating bit of quantum physics.
We are. We're looking at a specific chapter from the Feynman Lectures on Physics, Vol.3. It's called More Two-State Systems, and our mission really is to show you something quite profound.
Which is?
That things that seem totally different, like, an electron's spin or how light gets polarized, or even these really weird, strange particles, they're all described by the exact same, very simple mathematical framework.
It sounds almost too good to be true, like finding one key that unlocks a whole bunch of different doors in quantum mechanics.
That's a great way to put it. If a system basically has only two possible outcomes when you measure something specific about it, well, then its whole behavior can be mapped using these things called $2 times 2 matrices. Super efficient.
Right, the efficiency is key. Understand this one structure, this two-state system math, and suddenly you've got a handle on magnetism, light, particle decay. It's pretty wide-ranging.
It really is.
Yeah.
And the foundation for all of this, it rests on something called the Pauli spin matrices.
Okay, let's start there. The classic example Feynman uses is an electron in a magnetic field, right? Its spin is either up or down along a field. Simple enough.
Simple enough, yeah. And the energy tied up in that interaction, that's described by what we call the Hamiltonian matrix, often written as dollars. This matrix basically dictates how the probabilities or amplitudes for being up or down change over time.
And Feynman showed that building this Hamiltonian, this energy map, only requires four basic $2 times $2 matrix ingredients. That's right. You need the unit matrix or the baseline energy and then three others. The Pauli spin matrices, we call them sigma x, sigma y, and sigma z, sigmax, sigma a, sigma z, one for each dimension of space. These sound fundamental. What do they look like? Like sigma z, what does that represent physically? Well, mathematically, it's simple. It's got 1 and negative 1 on the diagonal zeros elsewhere. Physically, it just reflects the two possible outcomes when you measure spin along the z-axis. You get +1 spin up or -1 spin down. Okay, why these specific matrices? What's so special about the Pauli set? Well, this is where it gets really quantum. They capture something crucial. Measurements in quantum mechanics don't always commute. The order matters. Unlike classical physics, where multiplying 3 by 5 is the same as 5 by 3.
Exactly. But measuring spin along x then y gives a different result than measuring y then x. It's fundamentally uncertain. The Pauli matrices have this property built into their multiplication rules, like sigmax times sigma a doesn't equal sigma a times sigmax. In fact, sigmax sigma equals a sigmas.
That I is the imaginary unit, right? So complex numbers are baked right in.
They have to be. It's part of capturing that non-commutativity.
Right.
So these matrices aren't just convenient. They're sort of required by the physics. The electron's energy in the magnetic field, $1 mo math BFBR, translates directly into a Hamiltonian matrix, which is just a combination of these Pauli matrices weighted by the magnetic field components.
Okay, so the Hamiltonian is the energy recipe built from these fundamental Pauli ingredients. Now, how does the system actually, evolve? What's the rule for how it changes? That's the core dynamic equation. It looks like why fractum Prangle happen. It sounds complicated, but the idea is simple. The rate at which the quantum state changes over time is determined by the Hamiltonian acting on that state. So the Hamiltonian isn't just a static description of energy, it's also the operator, the engine that drives the change.
Precisely. It dictates the dynamics.
And the specific numbers inside the Hamiltonian matrix, the high G elements,
Yeah.
What do they tell us? You mentioned diagonal ones relate to the energy of the states themselves. What about the off-diagonal ones?
Those are crucial. They're the transition amplitudes. They tell you how strongly state I is coupled to state J.
Yeah.
So like how likely the upspin state is to flip to the downspin state and vice versa.
So a big off-diagonal number means lots of flipping back and forth.
Yeah, rapid oscillation between the states. If those elements are zero, the states are stable, they don't mix. These amplitudes are really the key concepts we'll see again and again.
Okay, fantastic. Let's put it to the test. First application, photon polarization. This feels very different from electron spin. One's about internal momentum, the other's about light waves. Seems different, absolutely. But from a quantum perspective, it's another two-state system. Think about the simplest ways light can be polarized. Horizontally, let's call out the 6-3 state, 6 wrangle, and vertically the I state 6 wrangle. Those are our two base states.
And any other polarization, say at an angle, is just a mix of those two.
Exactly.
Is a superposition. Light polarized at some angle, let's say 6 eta, relative to the x-axis, called 6 wrangle, is described as a combination. The amplitude to be found in state 6 wrangle is 6 eta, and the amplitude to be in state wrangle dal is 6 eta tal. So if you take that angled light, that sixth-angle state, and you pass it through a filter that only lets X-polarized light through, the probability gets through is just the square of the amplitude for the sextrangle state, which is for Arcadis.
And that's amazing because that crochet theta is exactly the rule Malus discovered classically centuries ago for how light intensity drops when passing through a polarizer.
Precisely. But here, it pops out naturally from quantum amplitudes and probabilities for a single photon. The classical intensity we see is just the result of billions of photons individually obeying this quantum probability rule. It's a beautiful connection.
It really is. And does this handle things like circular polarization too?
Yep. Circular polarization, where the electric field vector sort of spirals, is just another superposition of sextrangle and Young-Little, but this time the amplitudes involve complex numbers, representing a phase difference. The same two-state machinery handles it all.
Check, check. Light polarization, check. The math holds. Now for the big one, the really weird case Feynman tackles, the neutral K-meson. This involves particle physics, antiparticles, different fundamental forces. Surely this needs something more complicated.
You'd think so. It's definitely more complex territory. We're dealing with the neutral K-meson, KL or dollars, and its antiparticle, the anti-K-meson. The key property here is a quantum number called strangeness.
Strangeness. Okay, like a tag the particles carry?
Sort of. KL has strangeness +1, KL has strangeness max 1. Now, when these particles are created in high-energy collisions, it happens via the strong nuclear force. And the strong force absolutely insists on conserving strangeness. You start with 0 strangeness, you end with 0 total strangeness.
So if you produce a K-dollar doll S+1, you must also produce something with S1, maybe like its antiparticle or another strange particle.
Exactly. You start off with a pure beam, let's say, of the K-dollar particles. But then they decay, and decays are governed by the weak nuclear force.
And the weak force plays by different rules.
Completely different rules regarding strangeness. The weak force doesn't care about conserving strangeness. It happily allows a particle with S+1 to decay into particles with S0.
So the force that governs decay ignores the property that defined the particle at its creation. That sounds problematic for the particle's identity.
It is. It means the states that are natural for the strong force, K-dollars and bar, are not the states that decay simply or cleanly via the weak force. Gell-Mann and Pais figured this out. The states that have a simple exponential decay with a single lifetime are actually mixtures, superpositions of K-dollars a day.
Like finding new base states that are stable with respect to the weak force's Hamiltonian?
Precisely. We call these new states K-dollar and K-$2. They are specific linear combinations of K-dollars a day. And the mathematics, the same two-state Hamiltonian logic, predicts something truly wild about them.
What's that?
Their lifetimes are vastly different. K-dollars decays really, really fast, like in less than 10 seconds, usually into 2 pions. K-2, however, lives much longer, about 600 times longer, around $6 in time to 8 seconds, typically decaying into 3 pions.
Wow, a factor of 600 difference in lifetime just based on how KLR and TLRs are mixed together in the superposition.
Yes. It's a direct, measurable consequence of the two-state superposition dictated by the weak interaction Hamiltonian. But wait, it gets even weirder.
Weirder than a 600x lifetime difference. Go on.
Think about that beam of pure K-dollars we started with. Now, K-dollars itself can be written as a 50-50 mix of the fast-decaying K-$1 and the slow-decaying K-$2.
Okay, so as the beam travels...
The K-dollars part just disappears. Almost instantly, it decays away because its lifetime is so short.
Leaving only the K-dollar component behind.
Right. But remember, K-dollars is also a superposition. It's a specific mix of the original K-dollar and its antiparticle bar matter. So what started as a pure beam of K-dollar matter spontaneously evolves as it travels into a state that has a significant amplitude to be measured as antimatter.
Hold on. The beam starts as matter, and just by flying along, it starts turning into antimatter and back again. It oscillates.
It oscillates between being K-dollar and Takel. This isn't just math. It's experimentally observed. You can start with pure K-dollars, let them travel, and then detect K-dollars appearing in the beam. It's a macroscopic demonstration of quantum superposition and time evolution driven entirely by the fact that the decay states, K-dollars, K-2, are different from the production states.
That's absolutely mind-bending. And it all falls out of the same $2 times 2 matrix math we used for spin.
The very same core principles. It's probably the most dramatic proof in the chapter of how powerful and universal this simple two-state description is.
Okay, the universality point is well made, but, the real world often has more than 2 options. How does this elegant structure scale up if you have, say, n possible states? Does it just break down?
No, remarkably, the core idea is generalized very nicely. If you have n base states, your quantum state is now a list of n amplitudes, and your Hamiltonian becomes a bigger Noller times now matrix.
Instead of two equations describing how amplitudes change, you get n-coupled equations.
Exactly. The dynamic equation LE bar for eigenangle still holds, just with bigger matrices and vectors.
And finding the stable states, the ones with definite energy that don't change their fundamental character over time, like the K-1 and K-2 to refer to decay, how do you find those in an n-state system?
It's the same fundamental process, just scaled up. It's called finding the eigenstates and eigenvalues of the Hamiltonian matrix. You solve a specific mathematical equation. Det HIE, delta IG.
Okay, that looks like math, but what does it mean?
It's a condition that lets you find the special energy values, the Dillers, that the system is allowed to have. These are the eigenvalues, the quantized stable energy levels.
And for each allowed energy E, there's a corresponding stable state.
Yes, those are the eigenstates. They are the specific combinations, the specific superpositions of the original n-base states that correspond to those stable energies. They are the quantum system's natural states for that Hamiltonian.
Like finding the natural vibration modes of a complex object. That's a great analogy. And there's one more crucial mathematical property Feynman highlights. Eigenstates that belong to different energy eigenvalues are always orthogonal. Orthogonal meaning completely independent, unrelated.
Mathematically, yes. Physically, it means if your system is definitely in an eigenstate with energy EA, the probability of measuring it to have a different energy EA is exactly zero. They don't overlap at all.
Which is super useful, presumably. It means you can break down any complex state of the system into a clean sum of these independent, stable energy states.
Precisely. It gives physicists a guaranteed, complete, and non-overlapping set of building blocks to describe any state of the n-dimensional system. The core logic holds beautifully.
So let's recap for everyone listening. We went from a simple electron spin flip to photons passing through sunglasses, all the way to particles turning into their own antiparticles in flight.
And the incredible thing, the main takeaway, is that the mathematical heart was the same in every case. That Hamiltonian matrix structure, the Pauli matrices, or their n-dimensional cousins, superposition, finding stable states via eigenvalues, this is the universal toolkit.
So for you, the learner, this shows just how deep and consistent the foundations of quantum mechanics are. Once you grasp the two-state system, you've got the conceptual key to unlock surprisingly complex phenomena.
It means physicists encountering a new particle or interaction don't necessarily have to reinvent the wheel. They can often reach for these familiar tools, Hamiltonian, superposition, eigenstates, and make real predictions.
Yeah, it really is powerful. Okay, let's leave you with something to chew on, circling back to that truly bizarre K-meson oscillation.
Right. A particle beam spontaneously changing its identity, matter flipping to antimatter, just because it's a mix of two states, KD, KD2, that decay at vastly different rates.
An effect driven by the weak force's disregard for strangeness conservation. So here's the thought. What other weird, maybe seemingly paradoxical things in the universe might also be explained by a similar mechanism? Are there other situations, perhaps involving other forces or broken symmetries, where the true stable states are hidden superpositions of the states we normally think about? Could there be other kinds of oscillations happening driven by unstable components decaying away at different rates? What hidden transformations might be occurring right under our noses, just waiting for us to recognize the underlying two-state or n-state superposition?
It's a fascinating question, rooted directly in the physics we explored today.
Definitely something to ponder. Thank you so much for joining us on this deep dive into Feynman's insights on two-state systems.
It was a pleasure.
We'll see you next time.